This is a program about the Earth's most plentiful surface metal, aluminium. Every day we find thousands of different uses for this versatile, lightweight material. Things like car engines, racing bikes, TV aerials, compact discs, cooking foil, drink cans and aeroplanes. Even the TV you're watching probably contains aluminium. And as we'll see in this program, it's smelted from a white powder called alumina, using a chemical process called electrolysis.
Aluminium is what scientists call an active metal. That means it likes to react or combine with other elements. So you'll never find a lump of pure aluminium in the same way you might trip over a gold nugget. Instead, aluminium is always found bonded in a compound with other elements, inside surface rocks like this granite.
Granite is made of many different substances, including aluminium, silica, potassium, magnesium, iron, sodium and calcium. But how do we release the aluminium from its tight bond with these other substances? Fortunately, nature began the process a long, long time ago. "30 million years ago, a subtropical climate extended across most of Australia. High rainfall and the organic acids dripping from the lush vegetation began weathering the granite outcrops in some areas. Eventually, this process dissolved out and washed away many minerals, leaving behind a thick surface mantle of reddish soil. As well as iron oxides, it contained aluminium hydroxide, which forms when aluminium bonds with hydrogen and oxygen. Where this land was particularly well drained, like here in Western Australia's Darling Ranges, the iron oxides eventually washed away. So after decomposing for millions of years, all that remains are surface deposits of aluminium-bearing ore called bauxite. Bauxite's chemical name is hydrated aluminium oxide. It contains aluminium, oxygen and hydrogen. Because aluminium is a very active metal, it gives bauxite a melting point of over 2,000 degrees C. Smelting bauxite at these temperatures would be dangerous and costly because of the enormous energy required, and energy costs money. So instead of heat, we use electrolysis to eventually produce aluminium from bauxite. But for electrolysis to work, the bauxite must first be refined into alumina. This is Alcoa of Australia's alumina refinery at Pinjarra, Western Australia. It's one of 3 Alcoa refineries in this area, which together lead the world in alumina exports. Crushed bauxite mined from ore reserves in the nearby Darling Ranges arrives at the plant on a conveyor belt. Once here, Alcoa uses what's called the Bayer process to chemically filter out impurities such as iron oxide, silica and titanium oxide. It's an energy-hungry process, consuming about half the domestic gas supplied from Western Australia's North West Shelf project. The crushed hydrated aluminium oxide is mixed with sodium hydroxide, or caustic soda, in a high-temperature solution. During this reaction, the sodium hydroxide selectively dissolves the aluminium oxide into solution, leaving any undissolved impurities to be filtered out. Then the hot, concentrated sodium aluminate solution is cooled off and seeded with tiny crystals of pure aluminium hydroxide. This encourages further growth of these crystals. When there's enough, the larger aluminium hydrate crystals are filtered out and heated to around 1,000 degrees C. This intense heat drives the water off as steam, which is released to the atmosphere through chimney stacks. The refining leaves a dry, free-flowing sandy compound called aluminium oxide or alumina. Alumina contains small, highly charged aluminium and oxide ions held in a strong ionic network or lattice. Each oxide ion has an ionic radius 2.5 times larger than that of each aluminium ion. Because of this, and the 2:3 ratio of aluminium ions to oxide ions, with the like ions repelling each other, the lattice is very difficult to show in 3 dimensions. But Alcoa's research scientists believe that in order to maintain a charge balance, these ions are arranged in regular patterns in alternating layers. To make 1 tonne of aluminium, you need about 2 tonnes of alumina and just under half a tonne of carbon. Alumina from Alcoa's Western Australian refineries is shipped to Portland Aluminium in far southwest Victoria. It's unloaded with a large vacuum system and travels via an underground conveyor to a storage tank as big as the Melbourne cricket ground. American-made petroleum coke, a brittle solid containing over 80% carbon, is used to make the anodes consumed in smelting. The other major ingredient is electricity. In fact, aluminium is often called congealed electricity.
There are enormous amounts of electricity used to make aluminium. Around about 15 kilowatt hours per kilogram is a world average for aluminium, or for electricity consumption. That is the equivalent of a single bar, 1 kilowatt radiator, operating for 15 hours to make 1 kilogram of aluminium. It's a lot of power. For example, a smelter like ours, where we produce something around 900 tonnes of aluminium a day, our power bill is of the order of $500,000 per day.
Expressed another way, Portland Aluminium uses more than 10% of the total electricity generated each day in Victoria. This enormous power need is generated from the state's vast brown coal deposits in the Latrobe Valley, over 500 kilometres away. It's transferred across Victoria to Portland at 500,000 volts, a sufficiently high enough voltage to reduce transmission losses caused by this massive line's electrical resistance. At Portland, transformers drop the voltage to less than 1,000 volts direct current, ready for use. This is a recent independent summary of the average costs to produce aluminium in Australia. Raw materials like alumina are the most expensive ingredient, followed by electrical and other energy sources like gas or coal. Labour costs and overheads follow in third place. The heart of any smelter is its pot lines. That's the name given to the long lines of rectangular pots where electrolysis transforms alumina into molten aluminium. These pots are also called Hall-Héroult cells, in recognition of the Frenchman Paul Héroult and an American, Charles Martin Hall, who simultaneously but independently discovered an economic smelting method in 1886. Portland Aluminium has 2 pot lines, each with 204 pots like these, measuring 13 metres long by 4 metres wide. Current enters the line at one end, flows in series from one pot to the next, and exits at the other end. Then it flows through the second pot line, before returning to the switchyard to complete this massive circuit. Although these pots run at just 4.5 volts, the current is a staggering 300,000 amps. Compare this to the 80 amps used in an average home with every electrical appliance running. We can use this simple equation to work out the rate of power consumption at the smelter. Electrical power, or P, measured in watts, is determined by multiplying the voltage, V, with the current, I, which is measured in amps. So we multiply 4.5 volts by 300,000 amps to get 1,350,000 watts, or 1,350 kilowatts of power consumed by each pot. With 408 pots, plus power consumed by auxiliary equipment, the total plant power consumption is over 550 megawatts. This enormous power produces both the heat and electrolytic force needed for smelting. In these cross-section drawings, we can see how each cell or pot is constructed. A thermally insulated steel bottom is lined with large carbon blocks, which act as the cathode. These blocks are made from a very hard, high carbon content coal called anthracite and an oily coal pitch or tar, which are baked at high temperature. The carbon lining is negatively charged by the steel current conducting bars embedded inside them. Suspended above the cathode on an insulated superstructure are the carbon anodes, each weighing over a tonne. They're made from carbon-rich petroleum coke mixed with an oily coal pitch or tar, then baked at 1100 degrees C inside ring furnaces in the floor of this huge room. After cooling, the anodes are fitted with long copper rods to conduct current into them. The pot superstructure also includes a hopper for periodically introducing alumina into the pot below. And there's an overhead fume hood and removable doors to trap escaping gases and particles. For smelting, each pot is brought to operating temperature by electrical resistance heating. One way is to lower the anodes onto a layer of carbon-rich coke lying on the cathode, then turn on the current. The resulting short circuit heats the pot to 950 degrees C. The anodes then raised to leave a gap of about 50 millimetres, ready for the addition of the electrolyte needed for electrolysis. Electrolysis may be simply defined as the chemical decomposition of certain substances by an electric current passed through the substance in a dissolved or molten state. The electrolysis of alumina is done in a molten bath consisting mainly of cryolite or sodium aluminium fluoride, which melts at 1009 degrees C. But for greater efficiency, this temperature is reduced by adding aluminium fluoride and small amounts of calcium fluoride crystals and aluminium oxide. Alumina added to this electrolytic salt bath quickly dissolves, reducing alumina's normal melting point of over 2000 degrees C to a more economical 950 degrees. The cryolite forms a thick surface crust which further conserves costly heat energy. During a newly lined pot's early life, its carbon soaks up the electrolyte's sodium and sodium-rich fluorides, so workers add anhydrous sodium carbonate, or soda ash, to fix this imbalance. Aluminium fluoride is also added to match the sodium content of the consumed alumina. This maintains the correct weight ratio of sodium fluoride to aluminium fluoride found in cryolite. As electrolysis begins, these fluoride levels drop, partly because moisture in the air and the alumina cause hydrolysis, which produces hydrogen fluoride. This gas and other escaping fluoride particulates are collected by the fume hood and travel to a fluoride recovery system. Here the fumes pass through an incoming conveyor bed of alumina, which traps about 99% of these escaping fluorides and returns them to the pots. At any one time, alumina makes up about 3% of a pot bath's content. This level and the pot's voltage are carefully monitored by a computer, since any variations dramatically alter efficiency and airborne emissions. Electrolysis occurs when the electrical current combines with the heat energy to split the alumina dissolved in the electrolyte into its ionic components. the aluminium ions migrate to the cathode, where they pool at the bottom of each pot as molten metal. The oxide ions are attracted to the anode, where they react with carbon to produce carbon dioxide. Let's look at this reaction in more detail. For electrolysis to work, the very tight bonds holding the alumina lattice together must first be broken. This happens in the molten cryolite, which is one of the few solutions which will dissolve alumina. With the alumina in a molten state, its positively charged aluminium ions migrate to the cathode, which pushes excess electrons into these ions, making them neutrally charged. We write the reaction at the cathode like this. Molten aluminium pools on the bottom because it has a slightly greater density than the bath, and because this metal is immiscible in cryolite, in the same way as oil and water won't mix. The oxide ions are repelled by the negatively charged cathode, but attracted to the anode. Here they combine with carbon to form carbon dioxide and small amounts of carbon monoxide. We write the anode reaction like this. During electrolysis, carbon is being continuously ripped from each anode. So these decomposing anodes are automatically lowered into the bath to maintain the correct surface contact and current flow until each anode needs replacing after 4 weeks. The spent anode butt, as it's called, returns to the smelter's rodding area, where any remaining carbon and the copper conducting rods are recycled. Each year, the 2 pot lines consume about 180,000 anodes. The cathodes decompose more slowly and need replacing about every 5 years. We've now seen how electrical and heat energy cause electrolysis. The product is molten aluminium, which collects at the bottom of each pot. Every day, pot room operators use a siphon tube attached to a huge vacuum crucible to draw off this liquid metal. The crucibles are then carted to the nearby ingot mill.
The ingot mill is responsible for collecting the molten metal from the pot rooms and delivering it into the ingot mill. We've got 4 holding furnaces in the ingot mill where we place the metal and prepare it for casting. Now we just do a straight cast here. We don't alloy the metals, which requires different technology. So we basically just cast the metal into 22.5 kilogram ingots, stack those ingots into bundles of about 1 tonne, strap them up ready for shipment.
Operators here are specially trained to guard against hot metal burns. One preventative measure is to adopt Portland Aluminium's safety policy of never touching any metal with bare hands.
There is a number of hazards which are inherent in the process. We handle molten metal, which comes in at something like 950 degrees, and so that's always going to be hot. You're always going to get burned if you contact hot metal. During the process, we cast the ingots and they solidify at somewhere around 600 degrees, and the point with aluminium is it doesn't look any different when it's hot than when it's cold. It's always silver, unlike the steel industry. Hot metal is red and cold metal is black. An aluminium ingot, if it's hot, looks the same as if it's cold.
Quality control is crucial, so plant technicians test every crucible of metal for purity. They also continuously test every 10 tonnes of metal in the holding furnaces using a technique called optical emission spectroscopy. Metal purity averages 99.8%. The impurities comprise iron and silicon, plus traces of magnesium, manganese, gallium, chromium, zinc and vanadium. Each day, Portland Aluminium produces about 900 tonnes of metal, or 1 ingot every 2 seconds. In a year, that's around 330,000 tonnes, mostly for export. The metal's value varies between 550 and 900 million Australian dollars a year, depending on world prices. Australia's annual aluminium exports equal about $1.8 billion, ranking it next after wheat as our 8th most valuable commodity. Alumina is even more valuable in 5th position. But if you consider how much energy is used to change alumina into aluminium, is this value adding worth it?
It makes the metal relatively expensive. It varies in price from, depending on supply and demand, somewhere between $1,100 US per tonne up to $3,000 US per tonne, which makes it quite an expensive material. Because it is inherently valuable, aids in the recycling, or if you like, the return of that product. It makes it inherently cost-effective to recycle it. And in fact, it only takes about 5% of the original energy that was used to make it in the first place to convert it back into and reuse it again. And it can be reused over and over.
So how efficient is Portland Aluminium compared to the 15 other world smelters of similar size?
It varies depending on the technology and the age of the technology. On average, we would be, as a country, we would be amongst the most efficient in the world. We'd probably be second only to Quebec in Canada. Because our technology is, in the aluminium industry terms, relatively new. Our oldest smelter first started in 1956, and which was the Bell Bay smelter in Tasmania, and since then there's been considerable retrofit and advancement of that smelter. The majority of our capacity has actually been added since 1980. So more than half of our total capacity is, less than 12 years old.
And that means big energy savings converting alumina into aluminium.
The actual energy use has come down from in excess of, say, 50 kilowatt hours per kilogram back very early this century, down to now the very most efficient cells in the world operate down as low as 13 kilowatt hours per kilogram. I liken it to fuel consumption in motor vehicles, although the basic concept is still the same. There have been major advances.
Aluminium smelting consumes large amounts of electrical energy, which for Portland Aluminium is generated in Victoria's Latrobe Valley. But burning brown coal is a relatively inefficient method to generate electricity and produces large volumes of carbon dioxide. This significantly adds to Australia's greenhouse gas emissions. Aluminium smelters also release greenhouse gases, again mainly in the form of carbon dioxide. But smelter emissions of fluoride are often of more immediate concern, as demonstrated during the public consultation for Portland Aluminium's Environment Effects Statement, or EES. Fluoride is an essential ingredient in aluminium smelting. Like phosphate fertiliser producers and brick and glass works, aluminium smelters emit airborne fluoride pollution, either as a gas or in particle form. Most World Health authorities believe minute amounts of fluoride in our drinking water or toothpaste helps fight tooth decay. But extreme amounts can kill plants and adversely affect teeth and bones in animals and people. Before the smelter, Portland's Pivot fertiliser plant was already emitting fluorides, so a new smelter would add to this.
Hydrogen fluoride, which is the main concerning material, we have better than 99.9% collection of that, and that is returned back into the process, which I guess with like all good environmental things, when you're returning it back to the process, it's not only good for the environment, it's also good for the bottom line or the profitability, because it's expensive material.
For Portland Aluminium, Victoria's EPA has set a maximum emission level of 0.73 kilograms of fluoride per tonne of aluminium produced, equal to the lowest in the world. But the plant's filtering or scrubbing techniques often reduce this to as low as 0.37 kilograms per tonne. Even so, with annual metal production of about 320,000 tonnes, that's 122 tonnes of fluoride escaping to the atmosphere each year. So how are these emissions monitored?
Portland smelter has an extensive range of monitoring that is required of it. The EPA adopts a philosophy known as the polluter pays philosophy. We would argue that industries are not allowed to pollute legally, for sure, but it's really the onus of responsibility is on the company. They're the ones discharging the waste to the environment. They have the responsibility to be dealing with those wastes in an environmentally responsible manner.
Portland Aluminium's own monitoring includes regular sampling of air, water and land sources, as well as surveys on the health of local flora and fauna and domestic stock within the buffer zone. All results are checked by an external organisation called NATA, the National Association of Testing Authorities. Fluoride and other primary industrial pollutants, such as sulphur dioxide, are mostly dispersed by constant offshore winds. Even on still days, emissions are dispersed by the local atmospheric instability caused by rising heat from the smelter, a phenomenon called the heat island effect. But Alcoa's EES concluded that for about 20 days each year, when slight southeasterly winds blew onshore, pollutants would spread over land.
Oh, look at the black smoke over there.
Is that the bloody scrubbers or something?
The potential spread of pollutants became obvious during a fishing competition in 1988, when billowing palls of thick smoke spread across Portland. It followed a fire in an anode bake scrubber responsible for filtering sulphur dioxide and other particulates like carbon to an acceptable emission level.
In terms of pollution from the smelter, I guess we feel that we're doing an excellent job. In fact, we are a world benchmark for our emission performance on fluoride. I've certainly got to say that we believe we've got room for improvement too, and we've continued to improve our performance through time. There is some of our equipment that hasn't worked as well as we'd like and met our expectations or the community's expectations, in particular the baking furnace scrubber. And we haven't just sat back and said that's unacceptable. We've looked at how can we improve that situation, and we are doing things about that. In fact, we're investing $2.3 million on that particular piece of gear to have it meet and exceed our expectations and certainly the community's.
We've now seen that electrolysis is an expensive, energy-consuming method to change alumina into aluminium. And several important environmental questions regarding greenhouse gas and other emissions surround the operation of smelters worldwide. But for the time being, it remains the only viable way to produce one of our most important metals, aluminium.